Usually when we talk about like a medical diagnosis, there's this expectation of absolute precision.
Right, yeah. You want it to be definitive.
Exactly. Like you break your arm, the x-ray shows that jagged white line on the film, and the doctor just points at it and says, there it is.
It's a comforting kind of visibility. I mean, we really like things to be binary, broken or not broken.
Yeah. But when you step into the world of cloud data architecture, especially if you're the one building or scaling a massive app right now, that x-ray machine is just, well, it's fundamentally broken. You don't get a clean picture.
No, not at all. You're looking at this murky, endlessly shifting landscape.
And the danger of choosing the wrong database architecture isn't just that your application runs like a little bit slow, it's an actual physics problem at that point.
It really is. If you build on the wrong foundation, you can trap your entire engineering team in a total nightmare of latency, not to mention exorbitant costs that take literally years to unspool.
Which is exactly why we have to stop looking at these cloud services as just, items on a pricing menu. We have to understand the underlying mechanics.
Absolutely. So today, in this deep dive, we are stripping away the marketing jargon to fundamentally understand this massive paradigm shift happening in data architecture. Specifically, the decoupling of compute from storage.
Right. And to explore that shift, we're dissecting Google Cloud's data powerhouse trio. So that's AlloyDB, Google Cloud Storage, and Cloud Bigtable.
But we aren't just going to list what they do, because that's boring. We're going to tear them down to the studs.
Yeah, we want to understand why they work the way they do, right? And how they manipulate the physical limits of hardware to achieve that massive scale. So, okay, let's unpack this. I want to start with the relational side of the house.
Okay, the classic relational databases.
Yeah, we have an entire industry right now bleeding money, desperately trying to claw their way out of expensive proprietary legacy databases.
Well, for sure. You're talking about Oracle, SQL Server, DB2?
Exactly. They want open source. Basically, they want PostgreSQL.
They absolutely do. I mean, PostgreSQL has essentially won the developer mindshare. It's incredibly robust. But here's the catch. When massive enterprises try to forklift a decades-old, mission-critical Oracle workload into just, like, standard PostgreSQL, they almost always hit a wall.
Interesting. Why is that?
Well, standard PostgreSQL is fantastic, but when you are operating at enterprise scale, fantastic sometimes simply isn't fast enough.
Right.
You run into the absolute physical limits of how traditional databases handle input and output.
Okay, I have to challenge this right out of the gate, though.
Go for it.
If PostgreSQL has physical limits, and Google already offers Cloud SQL to run manage PostgreSQL, why did they go into a laboratory and invent a completely separate product called AlloyDB?
That's a great question.
I mean, if I'm an architect, spinning up a whole new service feels like taking on unnecessary risk when I could just, provision a bigger Cloud SQL instance with way more RAM and CPUs.
It's a completely fair challenge, but throwing more hardware at a traditional database architecture is basically a game of diminishing returns.
Because you eventually hit a ceiling.
Exactly. You eventually hit a massive I/O bottleneck. That's why AlloyDB isn't just a bigger virtual machine. Based on the benchmark data from our sources, AlloyDB is 4 times faster for transactional workloads than standard PostgreSQL.
4 times is a solid jump.
It is, but more importantly for analytical queries, it is up to 100 times faster.
Wait, 100 times faster?
Yes, 100x.
That sounds like a typo in a marketing brochure. I mean, if a complex analytical query, say, scanning millions of rows to find a specific purchasing trend takes a full 60 seconds on standard Postgres.
Which is an eternity in software, yeah.
Right. You're saying AlloyDB executes that same query in, what, half a second?
Less than half a second. 0.42 seconds in the benchmark examples.
Oh, wow.
Yeah, it turns a query that gives you enough time to go grab a coffee into a response that feels completely instantaneous to the end user.
Okay, so I assume they didn't achieve 100x speed up just by, tuning some configuration files. What did they actually do to the open source code to break the physics of standard Postgres?
Well, they didn't just tune it. What's fascinating here is that they fundamentally ripped the architecture apart.
Okay.
To understand this, think about a traditional database. The CPU, the memory, and the hard drives are all tightly coupled inside the exact same physical or virtual box.
Right. They all live together.
Exactly. When a transaction happens, say, updating a customer's address, the database has to perform what's called a block write.
A block write?
Right. It has to read a relatively large chunk of data from the disk into memory, update that one tiny piece of information, and then write that entire heavy block back down to the spinning disk or the SSD.
That sounds incredibly inefficient. It's like you're moving a whole filing cabinet just to change one single folder.
That is the perfect analogy, yes. And when you have thousands of users doing that simultaneously, the disk I/O becomes a massive traffic jam.
So how does AlloyDB fix the traffic jam?
So Google completely decoupled the compute layer from the storage layer. In AlloyDB, your compute nodes, which are the primary node, the failover, replica, read pool nodes, those servers actually processing the SQL queries sit completely separate from the storage.
Okay, so they pulled them apart.
Yes, they sit on top of a specialized layer called the Intelligent Database Storage Engine.
Intelligent database storage, and that's a mouthful.
It is, but it's crucial. And that engine itself is built on Colossus, which is Google's massive distributed file system.
But hold on, if you physically separate the CPU from the hard drive and put a network between them, doesn't that inherently introduce network latency? How on earth does adding distance make it 100 times faster?
Because they changed what travels over that distance. AlloyDB compute nodes no longer perform those heavy block writes. They only do log writes.
Log writes. So the compute node is just like shouting instructions.
Pretty much.
It just says, hey, I changed the address for customer 42 and sends that tiny memo down the wire.
Precisely. It fires off that tiny, lightweight log entry incredibly fast and just moves on to the next query immediately.
Oh, I see. So it doesn't wait around to pack up the filing cabinet.
Exactly. The Intelligent Storage Engine, which, remember, has its own massive distributed compute power. It receives that log and handles the heavy lifting of actually compiling the blocks, organizing the data, and writing it to Colossus in the background.
Wow. Okay. So the primary database node is freed from the burden of disk management entirely.
Completely freed.
That makes a lot of sense for transactional speed. You're offloading the busy work. But that still doesn't really explain the 100x speed up for analytics.
Right, because they're two different beasts.
Yeah. Transactions and analytics usually require fundamentally different data structures, right?
They do. Standard databases store data in rows. If you want to read one customer's entire profile, a row is perfect. But if you want to run analytics, like calculating the average age of 10 million customers, reading row by row is excruciatingly slow.
Because you have to load millions of irrelevant data points just to find that one age field in each row.
Exactly. Analytics databases vastly prefer columnar formats, where all the ages are stored together in one continuous block.
Which is why companies spend millions of dollars building extract, transform, and load pipelines, right? ETL.
Oh, the dreaded ETL pipelines, yes.
Yeah, they pull the transactional data out of the row-based database, transform it into columns, and load it into a completely separate data warehouse. It's expensive, the pipelines break constantly, and the data is always like hours or days out of date.
And this is where AlloyDB completely changes the architectural equation. It achieves what we call HTAP.
HTAP, hybrid transactional and analytical processing.
Exactly. It maintains the standard row-based format for those lightning-fast transactions, but simultaneously, it maintains an in-memory column-based format for analytics.
Simultaneously. But managing two different data structures sounds like an absolute nightmare for a database administrator.
It would be.
How do you even know which tables to turn into columns?
The beauty of it is, you don't have to know. AlloyDB handles this using machine learning.
Wait, really? The database does it itself?
Yes. The system's AI actively monitors your workload in real time. It watches the queries coming in, identifies which specific columns are being hammered by analytical requests, and automatically creates and manages those columnar structures in the available memory.
That is wild.
It's called auto-columnarization. The database is actively adapting its own physical memory structure to your behavior without you ever lifting a finger.
So it's basically a self-driving database. And this plays right into the whole autopilot philosophy we see all over the documentation.
Definitely.
Because anyone who has managed PostgreSQL in production knows it's like owning a classic car. You are constantly under the hood.
Constantly.
You're running vacuum processes to clear out dead rows, you're tuning memory buffers, but AlloyDB just handles the vacuuming, the memory management, and the storage tiering automatically.
And the crucial part is that despite all this advanced self-driving architecture, it remains strictly compatible with PostgreSQL-14.
So no weird proprietary query languages?
None. It supports 175 plus flags and over 50 extensions out of the box.
Yeah.
You don't have to rewrite a single line of your application's SQL queries. You just migrate an existing workload, keep using the same extensions, and instantly gain these HTTP capabilities.
Okay, so let's put this into a real-world scenario from the sources. Say
Mhm.
I'm an architect, and my company is running a massive e-commerce platform on-premise.
Okay.
It's Black Friday, transactions are absolutely flooding in, and my pricing team suddenly needs to run heavy analytics on live data to dynamically adjust our discounts.
A very stressful situation.
Very. And I can't wait for an ETL pipeline to run overnight. I need transactions and analytics hitting the exact same data simultaneously without dragging the checkout system down.
Right. So what do you choose?
Well, AlloyDB is the clear choice here. I wouldn't use Cloud Spanner because I'd have to rewrite all my application code to fit Spanner's unique relational model. And I wouldn't use BigQuery because that's purely an analytical warehouse. It's not built to handle high-speed Black Friday transactional checkouts. So AlloyDB threads the needle perfectly.
Exactly. It gives you the familiarity of Postgres with the power of decoupled distributed storage.
But here is the pivot. AlloyDB is our hyper-tuned relational engine. It is brilliant when data fits into neat, interconnected rows and columns.
Yes, the structured world.
But in the real world, most data just doesn't look like that. If I'm building a modern application, I have millions of high-resolution profile pictures. I have massive database backups, raw audio files.
The unstructured chaos.
Yeah. And if a junior developer tries to stuff a 4K video file into a PostgreSQL database, the senior engineers are going to have a literal heart attack.
And rightly so. Relational databases are designed for structured querying. They're not for hauling massive static binary files. For that, you need an entirely different architectural paradigm.
Which brings us to the cargo ships.
Exactly. You need an object store. And in Google Cloud, that is Google Cloud Storage, or GCS.
Now, I think a lot of people migrating to the cloud for the first time fundamentally misunderstand what GCS actually is.
Oh, all the time.
Because it has the word storage in it, they treat it like a giant hard drive in the sky. They think they can map it to their laptop, open a Word document, edit a paragraph, and just hit save.
That is a critical misconception. I cannot stress this enough. GCS is not a file system, and it is certainly not a database.
So what is it exactly?
Think of AlloyDB as a highly organized spreadsheet, right? While GCS is an infinitely massive warehouse where you can store anything from a single text file to a 4K movie, it is a flat, infinitely massive namespace.
Flat meaning no folders.
Exactly. You take an object, whether it's a 1 kilobyte text snippet or a 5 terabyte genome sequence, you put it in a bucket, and the system hands you back a unique URL.
And that URL is the only way you get it back.
That is how you retrieve it. There are no nested folders in reality, just long object names with slashes in them that sort of simulate folders for our human brains. And most importantly, these objects are fundamentally immutable.
Okay, wait. I really want to push back on that immutability aspect because honestly, it sounds incredibly frustrating from a usability standpoint.
A lot of developers feel that way at first.
Yeah, like if I have a 10 megabyte configuration file stored in GCS, and I discover a single typo on line 42, you're telling me I cannot just reach in, fix the letter, and save the file. I have to re-upload the entire 10 megabyte object just to change one byte?
Yes. You absolutely have to re-upload the whole thing.
Why on earth would Google design it to be that inflexible?
Because at cloud scale, flexibility is the enemy of consistency and speed.
Okay, how so?
Well, if GCS allowed in-place edits, it would have to implement incredibly complex locking mechanisms. Imagine thousands of servers trying to read that configuration file at the exact millisecond you are trying to edit it.
Oh, I see.
The system would have to halt all those reads, wait for your edit to finish, make sure propagated, and then resume. It would create massive bottlenecks globally.
So it's about guaranteeing the read speed.
Yes. By enforcing immutability, GCS guarantees that if you request an object, you get it instantly, and you are guaranteed to get the exact version that was written. No half edits. If you want to change it, you upload a new version that seamlessly overwrites the old one. It greatly simplifies the distributed physics of the system.
Okay, that makes sense when you view it through the lens of distributed caching and global consistency, but that immutability creates a new problem for us, managing the lifecycle of these files.
Right.
Because if files are constantly being overwritten or deleted, how do we handle legal compliance?
GCS provides very specific tools for lifecycle management. You really have to understand the tension between them.
The tension.
Yeah. The first tool is retention policies. This is your compliance hammer.
Hammer, I like that.
It is. If you are a financial institution and the SEC mandates that trading records must be kept for exactly 7 years, you set a 7-year retention policy on that bucket.
And once it's set,
Once applied, that policy is ironclad. Nobody, not the system administrator, not the CEO, not even Google support, can delete or overwrite those objects until the clock runs out.
That's intense. Okay, that's the rigid compliance side. But what about the recovery side? What if I'm not worried about the SEC, I'm just worried about my own developers accidentally deleting production assets?
Then you turn on object versioning.
Which does what?
When versioning is enabled, if you overwrite or delete a file, GCS doesn't actually destroy the old data, it just hides it and archives it as a previous version.
Yeah.
You can easily roll back if someone makes a catastrophic mistake.
But I'm assuming you can't have both. You can't have an ironclad retention policy that prevents all changes while simultaneously using versioning to track changes.
Exactly. This is a crucial architectural rule from the sources. You cannot have object versioning and retention policies on at the same time. They are fundamentally at odds.
So you really have to choose your priority for that specific data set.
You do. Do you need the historical flexibility to recover from mistakes? Or do you need the rigid, unalterable compliance of a retention policy?
Okay, so once we figure out the rules for the data, we have to figure out where it physically lives.
Location, location, location.
Right, because despite the ethereal name, the cloud is still just physical servers drawing power in concrete buildings somewhere. How do we choose the geography of our data in GCS?
It entirely depends on your application's architecture and your risk tolerance. You have 3 primary location types.
Okay, what's the first one?
First is regional. You pick one specific area, like us, Central 1 in Iowa. The data is replicated across multiple availability zones within that single region, so if one data center loses power, you are still online.
And the primary reason to use regional is the laws of physics, right? If my AlloyDB compute nodes are analyzing data in Iowa, I want my GCS storage bucket in Iowa.
Precisely. You collocate compute and storage for analytics.
Because I don't want to pay the latency penalty or the egress fees of pulling petabytes of data across the country from a bucket in California.
Exactly. But what if you aren't doing back-end analytics? What if you are serving video content to millions of users scattered across the globe?
Then regional wouldn't make sense.
No. Then you choose multi-region. Your data is redundantly distributed across a massive geographic area, like the entire European Union or all of Asia.
And that gives you, what, automatic failover?
Automatic geo-redundancy and failover, yes.
Yeah.
If a massive fiber cut takes out a huge hub, GCS automatically routes your users to a replica in another country without you ever lifting a finger.
That's incredible. And the third option is dual region. This seems like, I don't know, a hybrid.
It is a hybrid. Dual region lets you pick a specific pair of regions, say Iowa and South Carolina.
Why would I pick exactly 2?
You use this when you require the extreme performance of collocating your compute in your primary region, so you get that local speed. But your corporate disaster recovery policy legally mandates that a real-time copy must exist in a geographically distant location.
So it's the ultimate failsafe for collocated workloads. But building ultimate failsafes and storing infinite data gets expensive very quickly. Storing petabytes of data is a massive line item on a CFO's budget.
It absolutely is.
So here's where it gets really interesting. How do we optimize the cost in GCS?
By playing the cost game and matching the storage class to the temperature of your data.
The temperature, like hot and cold.
Exactly. GCS offers 4 tiers based entirely on how frequently you access the files. At the top is standard storage. This is your hot data. Website images, active analytics, streaming media.
Let me guess, it's the most expensive.
You pay the highest monthly storage fee, yes, but there is absolutely 0 cost to retrieve the data. You can access it 1,000,000 times a day for free.
Okay, then you step down to nearline.
Right. Nearline is for data you access maybe once a month. Think monthly reports, routine backups. The storage cost drops significantly, but in exchange, Google charges you a small data retrieval fee when you do access it.
And there's a minimum storage duration.
Yes, 30 days. You pay for at least 30 days, even if you delete it early.
Got it. And if we go colder...
Cold line. This is data you access less than once a quarter. Disaster recovery images, maybe raw footage from last year's marketing campaign.
Storage is very cheap, I assume.
Very cheap. But retrieval costs are higher. And finally, you have archive. This is the deep freeze.
The deep freeze. Data you access less than once a year.
Exactly. The storage cost is incredibly low fractions of a cent, but the retrieval fee is substantial. This is where you put data that you legally must keep, but hope you never have to look at again.
Now, managing that life cycle manually sounds literally impossible.
It is.
If I have a bucket with 50 million files, I can't pay an engineer to write scripts that check the last access date of every single file and move them between classes just to save a few pennies.
And you shouldn't. This is where you enable AutoClass.
AutoClass.
Yeah, AutoClass is a bucket-level feature that monitors the actual usage patterns of every single object.
So it does the checking for me.
Exactly. If a file isn't accessed for 30 days, AutoClass quietly transitions it to nearline. After 90 days, it moves it to cold line. 365 days, it goes to archive. It continuously optimizes your bill behind the scenes.
But the truly brilliant part is what happens when someone suddenly needs that data.
Yes.
Because if an auditor shows up and requests a file that has been sitting in archive for 2 years, AutoClass immediately transitions that object back to standard storage the moment it is read, ensuring high-speed access for the duration of the audit.
It does, though there's a caveat you have to remember.
What's that?
If you choose AutoClass when you create the bucket, you are committing to the system. You cannot manually set a default storage class later. You have to let the algorithm do the driving.
It's a completely hands-off approach to extreme cost optimization.
Exactly.
Okay, so we've mapped out this infinite, automated, globally replicated warehouse, but there's a glaring practical logistics problem here.
Getting the data in.
Yes. If I am an enterprise architect and I have 5 petabytes of historical data sitting on spinning hard drives in a private data center in Ohio, how do I actually get it into GCS? I can't just open a web browser and drag a petabyte folder into the upload window.
No, the physics of standard internet bandwidth would make that take a decade.
Exactly. So what's the process?
The logistics of data migration are where many projects completely stall. Google provides 3 tiers of tools depending on your scale.
It starts small.
Okay, if you are moving a relatively small amount of data, less than a terabyte, and you have a robust enterprise internet connection with good bandwidth, you just use GlueStill.
GlueSQL.
Right, it's a multi-threaded command line tool that efficiently pipelines the data directly into your buckets.
Okay, but what if I have 50 terabytes? Or what if I'm trying to orchestrate a massive migration from an Amazon S3 bucket over to Google Cloud?
Then you graduate to the storage transfer service. This is a fully managed serverless tool.
Serverless, meaning I don't spin up VMs to move the data?
Exactly. You give it the credentials to your AWS environment, or you install a small software agent in your on-premise data center, and the service handles the rest. Wow. It manages the network routing, it automatically retries dropped packets, it verifies checksums to ensure data integrity. You could even set it on a recurring cron schedule to continuously mirror an on-premise drive to the cloud every single night.
That's incredibly powerful, but what happens when the math completely breaks down?
Fun stuff.
Yeah. Let's say I have 500 terabytes of data. I'm a seismic imaging company, and my data center is out in a remote location with a terrible, heavily throttled internet connection. Pushing 500 terabytes over the wire is mathematically impossible in a reasonable time frame.
When you hit the absolute limits of the internet, you have to bypass the internet entirely. You use the transfer appliance.
This is one of my favorite concepts in cloud computing because it forces us back into the physical world.
It really does. You submit a request, and Google literally ships you a piece of hardware.
Wait, a literal truck pulls up.
A literal truck. It is a ruggedized, tamper-resistant, high-capacity server in a shockproof case. You wheel it into your data center, plug it directly into your local high-speed network rack, and you copy your data onto it at local internet speeds.
Which is way faster.
Way faster. Then you unplug it, put the shipping label back on it, and hand it to the logistics carrier.
But wait, we are talking about putting potentially hundreds of terabytes of highly sensitive, proprietary corporate data onto a delivery truck that is going to drive down a public highway.
Yeah, that sounds terrifying.
What if the truck crashes? What if the appliance is stolen at a rest stop?
Security is obviously the paramount concern here. Before a single byte of data is written to the disks inside that appliance, it is heavily compressed and encrypted using AES 256.
So it's scrambled.
Heavily scrambled. Even if someone stole the physical box and managed to pry it open, they would just find mathematically indecipherable noise.
But the really critical architectural detail here is what happens when the appliance actually arrives at Google.
Right, because Google doesn't know your password.
Exactly. So they plug it in, and the data doesn't just magically appear in your GCS bucket?
No, it sits there encrypted.
Yeah.
You, the customer, have to execute a process called rehydration.
Rehydration. Walk me through that.
You log into your Google Cloud console, securely provide the decryption credentials, and only then does the system decrypt, uncompress, and stream the data into your designated bucket.
And what happens to the box?
Once the transfer is verified, Google forensically wipes the appliance to strict NIST 800 standards before it is ever sent to another customer.
Speaking of encryption, this is the perfect segue to talk about how GCS secures data at rest in the cloud. Because putting your data on someone else's computers requires an immense amount of trust.
It does, and by default, GCS is uncompromising on this. Every single piece of data is 100% encrypted at rest and in transit.
You can't just uncheck a box and turn it off.
You cannot turn it off. The default state uses GMEK.
Google managed encryption keys.
Correct. Google's infrastructure generates the keys, rotates them automatically on a strict schedule, and manages the entire cryptographic lifecycle. It is completely transparent to the user.
But in enterprise environments, especially in highly regulated sectors like healthcare or finance, transparent isn't always acceptable.
No, they hate transparent.
Right. They don't want the entity storing the data to also hold the keys to unlock it. It violates the separation of duties.
For those organizations, you step up to CMAK, Customer Managed Encryption Keys.
Okay, how does that differ?
You use Google's Cloud Key Management Service, or KMS. The keys are still physically stored within Google's secure infrastructure, but you have complete control over the policy. You dictate when they are rotated.
And crucially, it gives you a cryptographic kill switch.
Yes. If you detect a massive breach, you can just revoke the key in KMS. The instant you do that, all the data encrypted by that key in GCS becomes instantly unreadable, even to Google administrators.
But there is an even deeper level of paranoia, or perhaps just extreme compliance, where a company refuses to let their encryption keys touch the cloud infrastructure at all.
And that is where we get to CSE, customer-supplied encryption keys. This is a paradigm that many other cloud providers simply cannot support.
Wow, really?
Yeah. With CSE, the encryption key is generated on your own on-premise hardware. You keep the key. Google never stores it on a disk, ever.
Okay, let's walk through the exact mechanics of this step by step, because it sounds like magic. If Google doesn't have the key, how do they encrypt the file when I upload it?
You provide the key in the exact millisecond it is needed, and only in volatile memory.
Okay.
Let's say you have a highly classified document. First, you generate a base64 encoded AES-256 key on your local machine.
Just a string of text.
Right. When you run the guide cloud command to upload the file to GCS, you explicitly pass that string of characters via the encryption key flag in the command line.
So the file and the key go up at the same time.
Google servers receive the file and the key simultaneously. They hold the key in RAM, just the RAM encrypt the file, write the encrypted ciphertext to the hard drive, and then immediately flush the key from memory.
So the only thing sitting on Google's hard drives is the encrypted garbage.
Exactly. Which means when you want to download that file tomorrow, Google cannot help you.
You have to provide the key again?
You have to run the download command and provide that exact same base64 string again. The server holds it in memory just long enough to decrypt the file and send it back to you.
This sounds incredibly powerful, but it also sounds like a loaded weapon.
Oh, it is.
What happens if a disgruntled employee leaves, a laptop gets wiped, and we lose that specific base64 string? We just call Google support and ask them to reset it, right?
If you call Google support, they will tell you they are terribly sorry, but they cannot help you. This is the terrifying stark warning of CSE. If you lose that key, you suffer what the industry calls crypto deletion.
Crypto deletion.
Yes. The ones and zeros representing your data are still physically sitting on a hard drive in a Google data center. But without the key, AES-256 encryption is thermodynamically infeasible to crack.
Thermodynamically infeasible.
Meaning all the computing power on Earth running for 1 billion years couldn't read that file. Your data is effectively permanently destroyed by math.
That is a staggering concept. That is the ultimate trade-off, right? Absolute control comes with absolute responsibility.
Exactly.
Okay, before we leave GCS, I want to briefly touch on network security. We've protected the data itself with encryption, but how do we protect the buckets from human error? We've all read the news stories about a junior engineer accidentally leaving an Amazon S3 bucket or a GCS bucket open to the public internet and leaking millions of user records.
It's the classic cloud horror story. Google provides organization policy constraints to build guardrails against exactly that.
What's the main one?
The most important one is enforcing public access prevention. You apply this at the organization level, and it acts as an absolute override.
So even if I'm an admin?
Even if a user with full permissions tries to make a bucket public, this policy blocks it. It ensures that data can never be accidentally exposed to the open internet.
And the second major guardrail?
Uniform bucket-level access.
How does that work?
Historically, GCS allowed access control lists, or ACLs, on individual files. You could say, make file A public, but keep file B private, all within the exact same bucket.
That sounds like a complete auditing nightmare. If you have 10 million files, how do you mathematically prove to an auditor who has access to what?
You can't. It's impossible. Which is why uniform bucket-level access disables those individual object ACLs entirely.
So no more per-file permissions.
Right. It forces you to manage security strictly through IAM policies at the bucket level. If you have access to the bucket, you have access to the objects inside it based on your IAM role. It is clean, it's auditable, and it vastly reduces the surface area for mistakes.
Okay, let's take a breath and summarize where we are. So what does this all mean? We started with AlloyDB, our decoupled relational engine solving the HTAP problem for structured data.
The sports car.
Right. Then we moved to GCS, our infinite immutable object store for unstructured blobs, media, and backups, the massive cargo ships where we manage lifecycle, costs, and the horror of crypto deletion.
But if we look at the landscape of modern applications, there's a massive gaping hole in our architectural strategy.
Exactly. What happens when the data doesn't fit either of those models?
What do you mean?
Well, what if we aren't storing static video files, but we also aren't processing perfectly structured financial transactions? What if we are dealing with an absolute fire hose of data?
Yes, the fire hose.
Imagine a global fleet of millions of IoT sensors on oil pipelines, or every single microsecond fluctuation of the global stock market. AlloyDB, for all its decoupled brilliance, is still a strict relational database. It would just buckle under the sheer volume of unstructured ingestion.
It would.
And GCS is an object store. It's too static. You can't query it fast enough to build a real-time dashboard.
When you are facing a massive fire hose of high-velocity data, you need a completely different paradigm. You need the hyperspeed bullet trains.
Cloud Bigtable.
Yes, Cloud Bigtable.
Let's define exactly what Bigtable is, because it has a sort of legendary status in the engineering world.
It really does. Bigtable is Google's fully managed, petabyte scale, NoSQL wide column database.
And it has a serious pedigree.
To understand its pedigree, you have to realize that Google literally invented this technology internally over a decade ago.
To run what?
To run Google Search, Google Maps, and YouTube.
Oh, wow.
Yeah. It is engineered with a singular, uncompromising focus on speed and throughput.
And the metrics reflect that. A single Bigtable node can handle 10,000 queries per second. That's per node.
Per node, yes.
With consistent 99th percentile single-digit millisecond latency. Let's translate that out of engineering speak.
Okay, translate it for me.
That means 99 out of 100 times you ask this database for a piece of information out of a petabyte-sized haystack, it hands it to you in less than 10,000th of a second. It is virtually instantaneous.
And because it is a wide-column NoSQL database, it has become the ultimate migration target for companies drowning in the operational overhead of managing their own Apache Cassandra, HBase, or DynamoDB clusters.
But incredible speed usually comes with incredible trade-offs, right?
Okay.
You don't use Bigtable to run a simple WordPress blog. What are the specific architectural scenarios where this is the only correct answer?
You use Bigtable when you have massive scale, high throughput ingestion, and require near real-time analytical access. Time series data is the classic prime use case.
Time series like server monitoring.
Exactly. If you are tracking the CPU, memory, and network usage of 3 million servers every single second, that is the Bigtable workload. Also, marketing data like purchase histories, high-speed financial tick data, and IoT data.
Let's visualize this diagnostic scenario. Imagine you are building the backend for a massive industrial IoT company. You have thousands of connected sensors on oil and gas pipelines around the world, streaming maintenance telemetry data continuously in real time. You need high scale and low latency. You need to ingest that data without dropping a single packet and instantly query it with a tool like Looker to build a live dashboard that predicts mechanical failures.
Right, so what do you build that on?
Well, the answer is Bigtable. If you try to put this in Cloud Spanner, the strict relational overhead will throttle your ingestion. If you try to use a document database like Firestore or Mongo, it just wasn't built for that raw, sustained throughput. Bigtable absorbs that sensor data effortlessly.
But as you said, there are trade-offs. And explicitly warning about the anti-use cases of Bigtable is just as important as knowing when to use it.
What is it explicitly not for?
Bigtable is not for relational data. It does not support SQL queries.
Wait, I can't just write a select where's statement.
Absolutely not. No SQL. And you cannot do a join operation.
Yeah.
Really. You cannot link a table of customer IDs to a table of customer addresses. Furthermore, it does not support strict ACD multi-row transactions.
Let's define that, because acidity is a foundational concept. Atomicity, consistency, isolation, durability.
Yes.
In a relational database, if I transfer money from my account to your account, the database guarantees that both my balance decreases and your balance increases simultaneously. If one fails, the whole transaction rolls back.
Exactly. Bigtable guarantees atomicity at the single row level, but not across multiple rows. It will not guarantee that an update to row A and row B happen simultaneously.
So if you try to build a banking ledger in Bigtable,
You are going to lose people's money. If you need OLTP multi-row AC transactions, you go back to Spanner or Cloud SQL. If you need OLAP, use BigQuery. Bigtable stripped all of that relational complexity out, specifically to achieve that single-digit millisecond speed.
so this raises an important question. If there are no SQL queries and no joins, how on earth do developers organize their data? How do you find anything in a petabyte of data without a query language?
You have to embrace NoSQL wide column design. Bigtable is fundamentally a massive distributed key value store. You have a row key, and that key acts as a singular address for a row.
Just one key per row.
One key. Inside that row, you can have thousands of related columns grouped into what are called column families. But importantly, it is a sparse table.
Sparse meaning what? If I define a column, but a row doesn't have data for it, does it take up empty space on the disk like a traditional database?
No. If a cell is empty, it takes up 0 bytes of storage. You can have a table with millions of distinct column qualifiers, but if a specific sensor only reports 2 metrics, you only store and pay for those 2 cells.
That's incredibly efficient.
It is. Because of this flexibility, a massive anti-pattern in Bigtable is creating dozens of small relational style tables. The limit is 1,000 per instance, but you should have far, far fewer. You actually want to denormalize your data. You put everything into massive, incredibly wide tables and let Bigtable sort it out via the row key.
And the row key is everything, right? Because if I want to find data, I can't just search the contents of a column. If I say, find me all rows where the temperature column is over 100 degrees, what happens?
The database has to perform a full table scan. It has to look at every single row across petabytes of data.
Yeah.
It will take hours, cost a fortune in compute resources, and completely destroy your latency.
So how do you query it?
You can only retrieve data efficiently by querying the exact row key, a prefix of the row key, or a contiguous range of row keys. Your row key design is the single most critical architectural decision you will make.
Okay, let me test a hypothesis here.
Test away.
If the primary use case for Bigtable is time series data like IoT sensors or stock prices, then it seems perfectly logical that I should obviously start my row key with a timestamp, right? Like timestamp sensor it. That way, all the data arriving right now is grouped neatly together at the bottom of the table, making it easy to pull the latest readings.
No. That logic makes perfect sense in a traditional database. But it is the absolute most catastrophic mistake you can make in Bigtable. You must never, ever start a row key with a timestamp or a sequential numeric ID.
Wait, vehemently correcting me here. Why? What physically breaks if I do that?
To understand why it breaks, we have to look at how Bigtable's architecture separates compute from storage, just like AlloyDB.
Okay, we're back to Colossus.
Yes. Bigtable's processing nodes sit above Colossus. The data in Colossus is divided alphabetically by row key into blocks called tablets.
Alphabetically, got it.
Each processing node is assigned responsibility for a specific alphabetical range of keys. Node 1 handles keys A through F, Node 2 handles G through M, and so on. Rebalancing happens automatically to reduce load on highly active nodes.
Okay, so the workload is distributed.
Exactly. But now imagine Bigtable as a massive commercial kitchen with 10 world-class chefs, which are your compute nodes. If you distribute the incoming orders, the writes by table number, Chef 1 handles tables 10-20, Chef 2 handles 20-30. Everyone works efficiently.
But if I start my row key with a timestamp,
You are handing out the orders strictly in chronological time. It's 12:00 p.m. By definition, every single order coming into the kitchen right now starts with 12:00. And according to your alphabetical sorting, all the 12.0 keys belong to Chef 5.
oh, so Chef 5 is hit with 10,000 queries per second and is completely overwhelmed, while the other 9 chefs are literally standing around polishing their knives doing absolutely nothing.
That is called hotspotting. You are pushing all sequential writes onto a single node. The system grinds to an absolute halt, your latency spikes to seconds, and the database fails, not because it can't handle the volume, but because you forced all the volume through a single pipe.
So how do you fix the row key? How do you store time series data without creating a chronological hotspot?
You force the distribution by preceding the timestamp with a high cardinality value.
High cardinality just meaning a variable with a lot of diverse, unique possibilities.
Exactly. For example, a user ID, or the unique ID of the IoT sensor. If your row key is sensor42 two-tag timestamp, then the data for sensor 42 goes to node A, the data for sensor 89 goes to node C, and the data for sensor 104 goes to node F.
The writes are instantly scattered evenly across the entire cluster. All 10 chefs are cooking.
Precisely.
What if I just run the sensor ID and the timestamp through a cryptographic hash function? That outputs a completely random string of characters. That would guarantee perfect, mathematically even distribution across all nodes, right?
Would guarantee perfect distribution? Yes, but it would create an absolute operational nightmare for your engineering team.
Why?
Because hashing destroys debuggability. If a specific wind turbine is sending corrupted data and an engineer looks at the Bigtable console to investigate, they won't see turbine 42. He will just see a chaotic string of alphanumeric garbage. You cannot decipher your own keys. So, use readable, high cardinality prefixes. Avoid hash values.
Okay, assuming we've designed our row key perfectly, let's talk about scaling. Because the compute nodes don't actually hold the data, they just process it and pass it to Colossus scaling. Bigtable has to be wildly different from scaling a traditional database.
Because of that decoupling, throughput in Bigtable scales entirely linearly. If you are hitting 100,000 queries per second and you need to hit 200,000, you don't need a complex migration.
What do you do?
You literally just slide a bar in the console to double the number of compute nodes. You can dynamically add or remove nodes without ever restarting the database.
There is zero downtime.
Zero downtime.
But there is a physics reality check here, right?
Right.
When you add a new node, it doesn't instantly absorb the load the very next millisecond.
No, the system has to realize the new node exists and begin rebalancing the tablets, shifting responsibility for certain row key ranges from the hot nodes to the new quiet node.
How long does that take?
Under heavy load, it takes about 20 minutes to see the full performance improvement of adding a new node.
Okay, good to know.
And conversely, if you scale down too aggressively, you force a massive rebalancing act that can cause temporary latency spikes.
To avoid engineers constantly riding the slider all day, you can just use auto-scaling, right? You just set a target CPU utilization.
Exactly. The recommendation is to target 70% CPU utilization. The system will automatically add nodes when traffic spikes and remove them to save money when it drops.
But while compute is highly elastic, there is one massive architectural decision you have to make when you provision a Bigtable instance that is completely permanent.
Storage types.
Yeah. You have to choose the physical storage medium for Colossus,
Yeah.
SSD or HDD, solid-state drives or hard disk drives. And, I mean, it's 2026. I feel like anyone building a high-performance cloud architecture would look at spinning magnetic hard drives as ancient history. SSD is the default answer for everything.
And 99% of the time, SSD is highly recommended. It is the correct answer. An SSD node holds a limit of 5 terabytes of data per node and guarantees that blistering single-digit millisecond latency.
So under what bizarre architectural constraint would you actually choose the spinning rust of an HDD?
You only choose HDD when you are dealing with massive data sets, strictly greater than 10 terabytes, and your application is absolutely not latency sensitive.
Why?
Because an HDD node has a 16 terabyte per node limit, which makes it much cheaper for massive storage. But the latency penalty is severe. We are talking hundreds of milliseconds instead of single digits.
So if I'm building a real-time dashboard for a user to look at, I can never use HDD because human perception notices a 300 millisecond delay.
Exactly. Any user-facing application mandates SSD. You only use HDD for something like an overnight batch processing job that runs massive analytics where nobody's waiting for the result in real time. And remember, this choice is permanent per instance.
You cannot mix and match them.
Never mix them. If you create an HDD instance, you cannot add an SSD cluster to it later.
Let's talk about availability and replication, because if I'm running a global IoT platform, this database has to survive regional disasters.
Right. Bigtable allows you to replicate your data across up to 8 different clusters, spanning up to 8 different Google Cloud regions. The max is 24 clusters total.
So I could have a cluster in Tokyo, one in London, and one in Iowa, all constantly synchronizing. But here is the critical distinction we need to make. How does Bigtable handle the physics of synchronizing data across the globe compared to a strictly consistent database like Cloud Spanner?
This is the defining trade-off of distributed systems. Spanner uses strict consistency. If you write a piece of data to Spanner in London, Spanner will not confirm to your application that the write was successful until it has coordinated with the atomic clocks and guaranteed that the data is readable in Tokyo.
It is incredibly safe, but it introduces the latency of the speed of light.
Bigtable refuses to sacrifice speed. So Bigtable uses eventual consistency.
Break that down. What does eventual consistency actually look like to the application?
If your application writes a sensor reading to the Bigtable cluster in London, the London cluster instantly writes it to disk and immediately says, "Got it," returning control to your application in 2 milliseconds. Then, asynchronously in the background, it begins replicating that data across the ocean to Tokyo.
Which means there is a tiny window of time where the Tokyo cluster is out of date.
Yes, usually it's just milliseconds, but if you have an application reading from Tokyo at the exact moment London is writing, Tokyo might serve the old data. It will eventually be consistent.
You trade absolute global synchronicity for absolute raw speed.
Exactly. And availability scales with clusters. A single cluster gives you 99.9% uptime. Multi-cluster routing in less than 3 regions gives you 99.99%. And multi-cluster routing across 3 or more regions gives you 99.999% availability.
5 nines. Before we close the book on Bigtable, we have to address security. Because earlier, we talked about how AlloyDB and standard relational databases allow incredible granularity. You can write a security policy that says, this specific analyst can only read this one column in this one table. Bigtable cannot do that, can it?
It cannot. The NoSQL structure doesn't support that level of intricate locking. Bigtable allows security at the project level, the instance level, and the table level via IAM, but it does not support row level, column level, or cell level security restrictions.
So once you grant a user or a service account read access to a table, they can read every single row and every single column within that table.
Correct.
So if I have a mandate that this Bigtable instance contains highly sensitive telemetry data and it must absolutely never be accessible from the public internet, even if a hacker steals a perfectly valid service account key, how do I secure it? IAM won't work because IAM just authenticates the key. It doesn't care where the key is being used from.
To solve the network access problem for ultimate network security, blocking the public internet entirely, the solution is VPC service controls.
How does that work?
You use it to create a service perimeter. You draw an invisible, impenetrable network fence around your Bigtable service. You define the perimeter so that it only accepts traffic from specific internal IP addresses within your virtual private cloud.
And if a request comes from outside?
If a request comes from the public internet, even if it holds the master key to the database, VPC service controls drops the connection instantly at the perimeter. It is the ultimate defense in depth.
That is an incredible journey through the architecture. Let's zoom out and synthesize the journey.
Let's do it.
So what does this all mean? We started by exploring the pain of legacy databases and how AlloyDB broke the physical limits of PostgreSQL by decoupling compute from storage, allowing us to use AI to achieve HTTP running transactions and analytics on the same data instantly.
Then we abandoned structure entirely and looked at GCS, an infinite object store, where we navigate the tension between immutable compliance and versioned recovery, fighting the physics of data transfer with physical appliances, and managing the terrifying reality of crypto deletion with customer-supplied encryption keys.
And finally, we tackled the absolute fire hose. Cloud Bigtable. Sacrificing SQL queries and strict consistency to achieve petabyte scale, single-digit millisecond latency, provided we understand the mechanics of NoSQL well enough to avoid chronologically hotspotting our compute nodes.
The big takeaway, the common thread across all 3 of these technologies, is Google's philosophy of separating compute from storage via Colossus. By separating the brains from the brawn, it allows unprecedented linear scalability and flexibility. It completely changes the physics of how we handle data.
It's a massive paradigm shift, and it leaves me with a final provocative thought to mull over as we wrap up.
Okay, what is it?
We've seen AlloyDB use machine learning to actively monitor queries and seamlessly reorganize its own physical memory into columnar formats. We've seen Bigtable automatically monitor CPU heat and transparently shift petabytes of data across processing nodes to maintain equilibrium. As these databases become increasingly self-driving and abstract away the underlying infrastructure, what will the role of the database engineer look like in 5 years?
That is a great question.
Right. Are we rapidly moving toward a future where we don't design databases at all, but simply describe our data's behavior to an AI that builds the architecture on the fly?
It's a profound evolution. We are moving from being mechanics who spend our days tuning the engine to being architects who simply define the destination and let the system build the vehicle to get us there.
It fundamentally changes the job description. Thank you for joining us on this deep dive into the architecture. To all of you listening, keep exploring, keep building, and keep questioning the data structures beneath your feet.